Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the API gateway, the single entry point that sits in front of every microservice in a modern distributed system. We'll cover how platforms like Netflix, Uber, and AWS handle routing, rate limiting authentication, SSL termination, caching, and request transformation, all in one component. Whether you're preparing for a senior engineering interview or building back-end infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the API gateway, the single entry point that sits in front of every microservice in a modern distributed system. If you have ever wondered how platforms like Netflix, Uber, AWS, or any large-scale SaaS product handle routing, rate limiting authentication, SSL termination, caching, and request transformation all in one place, this video is for you. We'll walk through the functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that define a senior system design interview answer. Whether you're preparing for a FANG interview or building back-end infrastructure, let's get into it. Here is the core problem. As an organization grows its backend from a monolith into dozens or hundreds of microservices, each service develops its own port, protocol, authentication scheme, and rate limiting policy. Clients, mobile apps, web browsers, third-party partners cannot be expected to know the address of every downstream service, manage separate tokens per service, handle retry logic themselves, or deal with different TLS configurations. Without a unified gateway, you get explosion of cross-cutting concerns spread across every service. Duplicate auth middleware, inconsistent rate limiting, missing observability, and a security perimeter that is impossible to audit. Every service becomes its own island. The business needs an API gateway that provides a single front door, enforces consistent policies, shields downstream services from client complexity, and gives the platform team full observability and control over every API call. Let's walk through the functional requirements. First, the gateway must support intelligent request routing, mapping each inbound URL path, HTTP method, and host header to the correct upstream microservice or service cluster, including version routing such as version 1 and version 2. Second, it must enforce rate limiting and throttling per client, per API key, per IP address, and per route, protecting downstream services from abuse and runaway clients. Third, it must handle authentication and authorization, verifying JWT tokens, API keys, OAuth 2 access tokens, and mutual TLS certificates before forwarding any request. Fourth, it must perform SSL termination, offloading TLS decryption at the gateway so internal services can communicate over plain HTTP inside a trusted network. Fifth, it must support response caching, request and response transformation such as header injection, body rewriting, and protocol translation, and provide rich observability through logs, metrics, and distributed traces. These 5 capabilities are the foundation of a production-grade API gateway. Now the non-functional requirements. Latency is the most critical constraint. A gateway adds a hop on every single request, so the added overhead must stay under 5 milliseconds at the 99th percentile. Throughput must support hundreds of thousands of requests per second, scaling horizontally without downtime. Availability must reach 5 nines because every downstream service depends on the gateway. If the gateway fails, the entire platform is unreachable. The gateway must be fault-tolerant, supporting circuit breakers, retries with back-off, and graceful degradation per route. Configuration changes, such as adding a new route or updating a rate limit, must propagate to all gateway instances within seconds without a full redeploy. Security must be airtight. The gateway is the outermost boundary, so it must resist DDoS, injection attacks, and malformed requests. Finally, full observability is non-negotiable, including structured logs, Prometheus metrics, and distributed tracing with OpenTelemetry. Here is the high-level system architecture. On the left, clients, mobile apps, web browsers, third-party partners, and internal services Send all requests to a global load balancer that distributes traffic across a horizontally scaled fleet of API gateway instances. Each gateway instance handles SSL termination, then passes the request through a sequential policy pipeline: authentication and authorization, rate limiting, request transformation, routing lookup, and caching. Approved requests are forwarded to upstream microservices, user service, order service, product service, payment service, via a service registry for dynamic discovery. Responses travel back through the gateway where response transformation and caching are applied before returning to the client. A configuration store, backed by ECT or console, holds all routing rules, rate limit policies, and auth configurations and pushes updates to all gateway instances in real time. A central observability platform collects logs, metrics, and traces from every gateway instance. The key metrics to memorize: cold request latency at the gateway, targeting under 5 milliseconds added latency at the 99th percentile. Throughput in requests per second, both sustained and peak burst capacity. Error rate, specifically the fraction of requests that result in a 400 or 500 response at the gateway layer. Rate limit rejection rate, which shows how often clients hit their quota and helps tune policies. Cache hit ratio for response caching, directly reducing backend load. Authentication failure rate, which can signal credential abuse or integration errors. And circuit breaker open rate per upstream service, which indicates how often the gateway is protecting a degraded downstream. These 7 metrics give you a complete real-time picture of gateway health and client behavior. Let's trace the end-to-end user journey. A mobile app user taps checkout in an e-commerce application. The app sends an HTTPS post request to the single gateway endpoint. The gateway terminates SSL, validates the JWT token attached to the request, checks the rate limit bucket for that client identifier, and finds the request is within quota. The routing engine matches the path/orders to the order service cluster. The gateway checks its cache. No hit for this mutation request. It forwards the request to the order service over internal HTTP. The order service returns a 201 created response. The gateway injects a request identifier header into the response, logs the full transaction with latency and trace context, emits a Prometheus counter, and returns the response to the mobile app in under 20 milliseconds end-to-end. The client never knew it was talking to a gateway. The core models and algorithms. The routing engine uses a tree-based or radix tree routing table to match inbound path patterns to upstream destinations in constant or logarithmic time, supporting exact matches, prefix matches, and regex routes with versioning. The rate limiter uses a token bucket or sliding window counter algorithm, with counters stored in Redis for distributed consistency across all gateway instances. The auth pipeline is a chain of validators: JWT signature verification, expiry check, scope validation, and optional RBAC policy evaluation. The circuit breaker tracks per upstream error rates and trip thresholds, opening the circuit to a degraded service and returning cached or fallback responses. The cache uses a content-aware keying strategy: request method, path, query parameters, and vary headers, with configurable TTL per route. Request and response transformers are pluggable middleware that operate on the header map and body buffer in a streaming safe way. The key trade-off is policy enforcement latency versus protection depth. More checks add microseconds but improve security and fairness. Now the low-level design deep dive. The gateway process is structured as an asynchronous event loop, handling each request as a pipeline of non-blocking middleware steps. TLS handshake offload, HTTP2 or HTTP 1.1 parsing, middleware chain execution, upstream connection pool selection, upstream request forwarding, and response streaming back to the client. The routing table is loaded from the configuration store at startup and updated in memory via a watch subscription, achieving zero downtime reconfiguration. Rate limit counters are stored in Redis using the token bucket pattern with a Lua script for atomic decrement and check, ensuring correctness under high concurrency. Auth tokens are validated against a cached JWKS endpoint, refreshed on a background timer to avoid per-request key fetches. The upstream connection pool uses keep-alive connections with configurable pool size, health check probes, and exponential backoff on failure. All request and response metadata is emitted as structured JSON logs and as labeled Prometheus histograms, with trace spans exported via OpenTelemetry to Jaeger or Zipkin. The configuration schema separates routes, policies, upstreams, and plugins, allowing surgical updates without touching unrelated parts of the config. Key takeaways for your interview. First, an API gateway is a reverse proxy plus a policy enforcement engine, not just a router, so emphasize the full pipeline: SSL termination, auth, rate limiting, routing, caching, and observability. Second, latency is the defining constraint. Every added check must be sub-millisecond, which is why auth caches JWKS keys, rate limiters use Redis Lua scripts, and routing uses radix trees. Third, horizontal scalability requires that all shared state, rate limit counters, cached responses, config, live outside the gateway process itself, in Redis and a distributed config store. Fourth, the circuit breaker pattern is essential to prevent a single slow upstream from cascading into full gateway overload. Fifth, config hot reload without restarts is a key operational requirement. Show how a watch on ECT or console triggers an atomic in-memory swap of routing tables and policy sets. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the API Gateway Deep Dive. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the API Gateway. We covered the full picture, from the core problem of scattered cross-cutting concerns, through request routing, rate limiting, auth, SSL termination, caching, and the low-level design of the request pipeline and config hot reload. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.